Hello everyone, I am Bhumika Emane. Today we are going to discuss about virtual memory. Let us move to the introduction to virtual memory. Virtual memory is a memory management technique that allows a computer to act as if it has more RAM than it actually has. The system uses secondary storage like a hard disk or SSD as an extension of RAM. The amount of memory a CPU can address depends on the number of address bits. For example, a 32-bit CPU can address 4 GB of memory even if actual RAM is less. Virtual memory gives an illusion of huge memory even when the physical RAM is small. Now let us discuss about physical memory versus addressable memory. Physical memory (RAM) is the actual hardware memory installed. The physical memory is usually smaller. The addressable memory is that total memory the CPU can access based on its architecture. For example, a system might have only 1 GB RAM, but 32-bit processor can address 4 GB of memory. When large programs don't fit into small RAM, it means the extra data is stored temporarily on secondary memory. For secondary memories like hard disk and SSD, RAM is limited, but CPU can imagine more memory space, and virtual memory fills this gap. And let us know about how virtual memory works. Virtual memory divides the program into small chunks. It means it divides the program into small parts. Only the currently needed part of program stay in RAM. If is full and new part is needed, the system swap out an old part from RAM to disk and load the new part from the disk to RAM. It means when the process is done, the system remove the old part and the next part what have to done is move to the RAM. This entire process is automatic. Programmers do not need to handle memory movements manually, but they should know that how much swapping slow the system. It means there is too much of swapping so the system. That means called trashing. Only useful part stays in RAM. Old parts are moved out of make space. Now let us move on to the next slide, that is virtual memory techniques. In this slide, we are going to discuss about virtual memory techniques. These techniques ensure smooth movements of data between RAM and secondary storage. The OS checks which part of the program are active. Only active parts are kept in RAM, inactive parts are stored on disk. This improves performance even when physical RAM is small. In simple words, virtual memory keeps only what is needed in RAM and moves the rest to disk. And next is address translation in virtual memory. Programs do not use physical memory address directly. Instead, program generate logical it means virtual address. This address must be translated physical RAM address. The translation involves hardware and operating system. These translations happens constantly and very fast, is completely invisible to user. Now let us simply know the flow of this. Virtual address followed by MMU plus operating system, and next convert them to physical RAM address. Let us know about when virtual memory is used. In VR, there is a two cases. In case 1, requested data is in RAM. Virtual address is translated, data is accessed instantly. Here in requested data, when it is in RAM, this process is fast. In coming to case 2, requested data is not in RAM. If a page fault occurs, OS find the data on disk, loads it to RAM, then continuous execution. Hence, this is quite long process than case 1. Here, the slower the process. For example, if data is in RAM, it's use it. But if not, brings it to disk, then use it. In final, virtual memory makes RAM looks bigger than it is, along with stores extra data and secondary memory, and it automatically moves data in and out of RAM, uses virtual address that are translated to physical ones, ensures programs runs if RAM is small. Thank you.
Good evening. I'm Sanjana M. So now we will know about the virtual memory organization. So this diagram shows how the data will transfer inside a computer using a virtual memory. Coming to the processor always generates a virtual address, which is not physical address. So the virtual address it cannot be it cannot be accessed by the RAM because the RAM uses the physical address. And next coming to the MMU, which is memory management unit. The virtual address it goes to the MMU, and then MMU job is to convert the virtual address into the physical address. And if the required data is already in the RAM, then MMU it will fetch it quickly. Otherwise, it should be transformed from the secondary memory to the main memory. And next cache, so it is one of the small storage where after the address is translated, the processor it tries to read the data from the cache, and the cache is very fast memory. And same if the data is found in the cache is and it will access very fast. And if not, cache will miss, and the page goes to the main, and then it will goes to the main memory. And coming to the main memory, which is RAM. If the data is present in the RAM, then it is returned to the processor. And but if the page is not present in the RAM, the page falls across. And disk storage, which is a secondary memory, when the data is missing from the RAM, then it is taken from the disk storage, which is nothing but the hard disk, and the transfer from the transfer from the disk to the RAM it happens using a DMA, which is direct memory access. And after the data, it is the page is loaded into the RAM, and the processor can finally use it. So the simple thing is the first the processor will send the virtual address to MMU, and then MMU then it will convert it into the physical address, and then cache will receive it, and then the main memory, and lastly the disk. Next coming to the next slide. So here we will discuss about what is page frame and all, and this also how the virtual memory works inside a computer. So the processor always generates, as I said in a diagram, and then the MMU which converts the virtual address in the physical address. Next, finally after that, the data will reach to the main memory. Uh, this slide will explain how paging works in the virtual memory. So, give me a minute. Next, coming to the what is page frame is the area of the main memory which can hold the page is called the page frame, and what is page is now let us know about what is page. The program or a data which they are composed in a fixed length unit which is called as page. And the page consists of a block of words which occupy the contiguous location. Means the pages will be stored in the continuous memory location. It can it is not be scheduled. And the page is a basic unit of an information which can be transferred between the secondary storage and the main memory. Means this will share the information between storage and the main memory. And next coming to the next slide. Now we will know about the how the page will work here. And so the commonly ranges of size of the page is ranges from 2K to the 16K bytes, because if the page is too small, it can't be fixed in the block. If it is too large, the memory needed a large space to store it. And then the page table it keeps information about where each page is stored in the memory. Uh, then each address will generated by the processor, and CPU will generate a virtual address which consists of a page number which is of high order bits and offset which is of low order bits specifically. Page number means it identifies the page, and offset means it identifies the exact byte where we have to search. And next, the page frame, the area in the main memory where page can be stored, it is called page frame. In the starting address of a page table, it is kept in the page table base address. And next, this page entry will tell the where the page in the memory and it gives its physical address. The contents of this location in the page table, it can be give the starting address of the page if the page is currently in the main memory. Thank you.
Good evening, everyone. I'm Varsha. So now let us know about virtual memory address translation. So what it means is it is a mechanism used by the OS, that is operating system, to convert a virtual address generated by CPU into a physical address in the main memory. In short, virtual memory address translation, it translates the virtual address into physical address. Now let us know the process, how it is work in this diagram. So here the CPU issues the virtual address. Here you can see a box. It is split into two parts, that is the virtual page number and the offset. So you can think the VPN as the page label, which page we need, and the offset as the exact position inside that page, like index within the page. So now on the left, here we can see there is a page table based register. It holds the starting address location of the page table in the memory. So the diagram shows a plus sign here. So this means we use the PTBR together with the VPN to find the one specific row in the page table. So the hardware calculates PTBR plus VPN to produce the address of the correct page table entry, that is PTE, inside the page table. Now, we do this because every virtual page has a corresponding entry in the page table that tells us where the page actually sits in the physical memory. Now here you can see the selected page has divided into two parts, that is control bits and the page frame in the memory. So the control bits indicates the page status. For example, a valid bit, like is the page currently in the RAM? A modified bit means the page has been modified after it is loaded into the system. And there is a protection bits means read or write permissions. So though this diagram does not list each name, but its labeled column is where those status flag lives. So the page frame is nothing but the physical page number, the actual frame in the RAM where the virtual page currently resides. The page frame value is sent to the box. You can see here that's the page frame. So the offset from the original virtual address travels straight down to the here. So the offset is unchanged by the lookup because the offset specifies the location inside the page and the internal position stays the same whether the page is virtual or not. Finally, this diagram combines the page number and offset to form the physical address in the memory. So the final box at the bottom is the exact physical location the CPU will access. So this is what I explained before. Now let us know the key points about the page table. So, as I said before, the control bits has the three bits, that is the valid bit, modified bit, and the permission bits. Valid bit means it indicates whether the page is currently in the physical memory. So, if the valid bit is 1, the page is present in the RAM, CPU can access it. If the valid bit is 0, page is not in the RAM, it leads to page fault. It is used because it prevents the CPU from accessing pages that are not loaded. Next is the modified bit. It shows whether the page has been changed after loading. So if the modified or the dirty bit is 1, the page was modified, it must be written back to the disk before removal. If the dirty bit or the modified bit is 0, page is unchanged and it can be removed without extra disk write. It helps avoid unnecessary and slow disk operations. Next is the permission bit. It defines the allowed permissions like read, execute, and write. Protects memory from illegal access or accidental corruption. For example, a code pages are usually read only, and the data pages allow read or write operations. Next is the page frame number. It identifies the exact physical frame in the RAM where the page is stored. VPN selects the page entry, and PFN, page frame number, is combined within the offset to generate the physical address. Without FPFN, the CPU cannot locate the actual data in the RAM. So the where the page table is actually stored, the entire page table is kept in the main memory because it can be very large. Every process has its own page. Next, each process has its own page, and the CPU uses the page table register to locate it. So the hardware uses PTBR plus VPN to reach the correct entry. Thank you.
Good evening, everyone. I am Varsha. Here I'm explaining use of an associative mapped TLB. It explains how a computer converts a virtual address into a physical address using the TLB. TLB means the translation look aside buffer. Uh, Next, move on to the next slide. Address translation using the TLB. When a program runs, the CPU does not directly use physical memory addresses. Instead, it generates a virtual address. The virtual address has two parts: the virtual page number VPN and the offset. Offset means it is a constant. The virtual page number is sent to the TLB. Next, the TLB means it is a small, fast memory access memory. It stores a recent virtual address to physical address translations. Next, the system checks if the virtual page number matches any entry in the TLB. If a match is found, it is called as TLB hit. It means the corresponding page frame number is immediately obtained. The physical address is then formed by combining the page number with the offset. And this process is very fast. If there is no match is found in the TLB, it is called the TLB miss. In this case, the system must check the page table in main memory. It is a very slower method. And the most modern processor use set associative TLBs because they offer a good balance between speed and hardware cost. And next, move on to next slide. The page fault and OS handling. It explains what happens when the required page is not present in the main memory. It is known as the page fault. A page fault occurs when the CPU tries to access a page that is currently stored on the disk instead of a RAM. When this happens, the MMU, means the memory management unit, detects the fault and immediately raises an exception. The running program is When it raises an exception, the running program is temporarily stopped and control is handed over to the operating system. That operating system finds the required page in secondary storage, such as hard disk, RAM, and it loads the entire page into main memory. Once that page is loaded, the page table and TLB are got updated, and the program resumes exactly from where it is paused. Although a page fault slows down ex- execution, it allows the system to run the programs that are larger than the available RAM. Thank you.